Hello. Well, I haven't made a lot of videos recently because the weather has been so appalling. I haven't done a lot of flying and haven't had anything to show. I've got a few things I want to do, but I've been quite tied up with the Chibios upgrade for ArduPilot and then working on supporting external flash in the STM32 H730. So yeah, I've been doing a lot of coding type stuff, but not much flying type stuff. But spring is here, the weather is getting a bit better, so hopefully I'll do some more soon. And I've been given loads of nice kit by hwdef in particular, so hoping to do some video on companion computers and building a couple of different drones, video on my T1 Ranger when I get to that. Anyway, all good stuff, all in the future. But I thought I'd better make some kind of video right now of something that would be interesting to people. And what I try and do in this channel is just cover stuff that might be a little bit more complicated and that people don't necessarily understand. And so what I thought I would do is walk through the hwdef format. So hwdef is the is a DSL effectively. It's domain-specific language for specifying flight controller pin mappings and layouts. It can be a little complicated to understand, but it's not that complicated. And I get a lot of questions about this, and so I thought I'd just do a little walkthrough of a particular hwdef that I did, and then you can see. So, first of all, where are the hwdefs? Well, you can see here that so here's one for a Kakut H7 Mini. So I got hwdef.dat, and that's the main firmware file. And then there's actually one called hwdef-bl.dat, which is the bootloader definition. And these names are important. So -bl is what is looked for when building bootloader, and hwdef is what looked for when building regular firmware. And this name is important, this directory name is important, Kakut H7 Mini. So WAF, which is what you use to build ArduPilot, I'm not going to do a WAF tutorial here, but if you say WAF -- configure and then a board name, it's this folder name that is important for that board name. And this lives in this directory, libraries, APHEL, Chibios, hwdef. Very, yeah, I would love it if this was changed somewhere higher, like to a top level, but this is just where it is. It's quite hard to change, so sorry. I'll just look through the bootloader one first, because bootloader definitions tend to be a little bit easier because they're not doing very much. So here is the bootloader for Kakut H7 Mini. And the first thing to notice is that we specify what chip it's using, and in this case it's an H7 chip, and it is in particular an H743 family of chips. Now this is important not just from a kind of, various definitions hang off of this, so the code might define stuff based on what chip family it is, but also there is a chip definition file written in Python that this one in particular specifies. So so when this file gets processed by configure, it will the sort of configuration script will look for a Python file with this name, and these files live in another really interesting location, scripts. So we've got libraries, APHEL, Chibios, hwdef, Kakut H7, script. Let me pick the one I'm looking for. H743. Okay, scripts STM32 H743 xx.py. So this is the same name as in hwdef.dat, and this is the script that specifies stuff for the chip. Now, you don't need to know an awful lot about this, you just need to know it exists. And there's various things about how the memory is laid out, how it's built in Chibios, some flags related to compilation. You can play with these if you want, but sort of here be dragons. But the interesting thing is this function map. So this specifies the allowable functions for pins on the chip. So and this file is generated from the STM32 datasheet. So for instance, let's say you specify a pin, PA, these are pins. So pin A0, let's say you specify that to be timer 2 channel 1, and this is allowed because it's in this map. But if you specify a pin to be timer 2 channel 3, PA0, you'll get an error because it's not in this map. So all the PA0 definitions are here. These are the allowable functions for PA0. These are the only allowable functions. And so if you get errors defining saying, oh, this you can't assign this pin, it's because it's not in the map that's allowed. Okay, so these are all you can see loads and loads and loads and loads of pins. Just this is basically the whole file. Is all of these pins. Don't need to know about what the alternate function is. And then the other thing to know, okay, so this is the ADC map, which specifies the pin to, so the MCU pin to the analog pin, which is the thing you might specify in config here. So this is a mapping from MCU pin to analog pin. And what you'll notice is on the H7, that's it, okay? But in other, and that's because the H7 has very flexible DMA mapping. So you see DMA map is none. If you look at F7, F4, not very flexible DMA mapping. So if we have a quick look at F4, same function definitions. If we zip to the bottom, here we go. So here's the DMA map. So these are all of the allowable DMA channels for a particular function. And so if you want DMA on SPI1 RX, the only DMA channels you can use are 20 and 22. So this third number is not really that relevant. It's this first number that's relevant, 2022. And these, if you get sharing with DMA, you may have heard of sharing. So for instance, let's try and find one that might make sense to share. Okay, so SPI4 RX20 and SPI1 RX20. So these could potentially share a DMA channel, except that we don't allow sharing on. No, they could potentially share a DMA channel. So SPI1 and SPI1 RX, SPI4 RX could share DMA channel 20. So these are the DMA channels. You can see fairly limited, and when building HWDF, this can often be the limiting factor on non-H7 boards. On H7, much easier because basically you can have any DMA channel mapping you like. Okay, so back to the bootloader, wherever that is, not that file. Here we go. Okay, Qt H7 Mini bootloader pins. Okay, so we've got our MCU type, and then whoops, we have a board ID. So the board ID is the thing that Mission Planner looks at when matching bootloader to firmware. So this board ID in the actual firmware needs to match the bootloader ID. Otherwise, Mission Planner won't let you load what it'll say invalid firmware for bootloader. And this board ID, there's a list of these that lives in Tools. tools, AP bootloader, board types. So you've got tools, AP bootloader, board types. And you can see there's Kahoot F7 here, and somewhere here is Kahoot H7. Clearly spelling something wrong. Kahoot F7. Not sure why it's not in there. That seems like a mistake. Anyway, yeah, it does seem like a mistake. You could search for the board ID. Let's have a look at the board ID. 1058. Oh, it's in lowercase. Kahoot H7 Mini here. So this is the board ID, and this. Although this file is not checked automatically, it is checked by the developers to make sure that board IDs are unique. So that's the board ID. Next up is the frequency of the oscillator. So this is set in hardware. This is what your vendor, when he builds the flight controller, he uses a little external oscillator, and you just need to know what this is. 8 megahertz is fairly typical. Some of the higher end boards use higher than this, 16, 24, 25, but 8 megahertz is fairly typical. Then you got the size of the flash chip, 2 megabytes, fairly typical, or you might have 1 megabyte. And then you've got this flash reserve start, which basically says whether to allocate a little bit of flash at the beginning of the chip for other stuff. And for a bootloader, you don't want to do that. You want the bootloader to start. And then you also want to tell the bootloader where the main firmware starts. So this main firmware starts at 128K. So the bootloader is basically takes 128K. That 128K is not available in the flash for flight control software. It has to be used by the bootloader. So one thing to note is why this magic 128K number? The different STM32 chips have different sector sizes in flash, and you can only write sectors all in one go. So, sorry, that's not quite true. You can only erase sectors all in one go. So flash memory is kind of write once type memory. You basically have to erase a sector and then write to it. The sector size that you can erase differs between chips. And on the H7 it's 128K. On the F7 it's 64K, and on the F4 it's 4K, I think. So a bit more flexibility there for F4, which is why you'll see smaller bootloaders. But for H7 it's 128K, and so that's the smallest sector size you can have, and therefore the smallest bootloader size, because you want to be able to erase the bootloader separately to other stuff, and vice versa. We then got the storage size. So this is the amount of memory, flash memory basically available for parameters. And because of the large sector size, we can set the storage size quite high. And then really the only definitions you need for the bootloader are the USB device. And so we have this serial order, which talks about UARTs, serial ports. And the only thing the bootloader cares about is the USB device, which is called confusingly OTG1. Yeah, you may have, like with Android and stuff, you may have heard USB referred to as OTG, and that's how it's referred to in the hwdef. And then we have our first serial port definition, and so this is for OTG1, and this basically says pin A11 is mapped to this function, OTG.FSDM, and that is for this UART, OTG1, and similarly for for PA12. And if we look for this function, OTG.FSDM, in the script file, we saw earlier, we'll find that it is there. Okay, and so you can see PA11 is allowed to match to HEGFS DM, and similar for the other ones. So DMDP, these are just specific USB functions. You don't really need to know what they do. But worth noting that almost all boards have PA11 and PA12 as USB pins. It's sort of almost universal. We then got a couple of pins for debug, which developers like to put on so they can debug the bootloader. And then we've got another pin definition, which is for the buzzer. This is, so now what you can see here is this is not a function defined in the script, so you won't find buzzer in this STM32H743. This is an ArduPilot definition, and so this will be a general, I think, GPIO pin, or something is known about this, what this pin function should be. And so, GPIO, any pin can be a GPIO pin essentially. But the reason it's in the bootloader is we don't want the buzzer going off while the thing is booting. And some boards need the buzzer pin pulled low, some of them need them pulled high in order for the buzzer to be off. And so this is what this is achieving: pull the buzzer pin down so that it's off during boot. And similarly with LEDs, let's have the LED on while we're booting. So again, this is a ArduPilot function definition, not a STM micro definition. Similar sort of idea. And then all of the other pins we're just going to pull low because you can get weird like servo movement and stuff like that. So this is again is an ArduPilot. Let's pull the pins all low to avoid some issues. Apart from the chip select pins for the devices, so in general, chip select pins for devices, SPI devices, these need to be pulled high in the bootloader in order to initialize properly. And so this is a sort of universal pattern. And then on this particular board, there's actually a pin that determines whether there's power to the VTX or not. And we want to make sure that there's power to the VTX pin or pad on startup, and so this is why this is pulled high. So that's the bootloader definition. So this is what will get read if you build firmware with the -- bootloader option, and it's pretty simple, as you can see. So then on to the main hardware definition. So you can see it's pretty similar. So all of these are the same. And then we come down to some more involved stuff. So, for instance, so this says for Chibios, which is the sort of operating system that we use, it's sort of timer, like it has a notion of system time. And this says use timer 12 for system time. And it says that the resolution of this timer is 16-bit. So a lot of timers are either 16-bit or 32-bit, and so timer 12 has 16-bit resolution. I think the default, Chibios has some defaults. You don't always need to set these. Chibios has some defaults for timers. For the system timer, I think it's 5 for H7, so this is just changing it from the default because we want to use timer 5 for something else. So that's why this is here. And then you can see that we're going to reserve a bit of flash at the beginning because we need to make sure that there's space for the bootloader. So that's why. So if you remember, flash reserve start was 0 in the bootloader, but it's 128 here because we need to reserve space for the bootloader. Same storage size, but then interestingly, we now have to specify where the storage is. So storage typically lives on 2 flash pages. Because the way storage works is you write storage to one flash page, and while you're writing, the other ones can be read, and then once you've sort of updated, you switch them over. And so this kind of write stuff, switch over, erase the one you're no longer using, switch back, and we keep doing this kind of thing to write parameters to flash while giving good availability, while still kind of observing what the flash requirements are. And so those two pages that get switched have to be a page. So we have on a H7, if you remember, page size is 128K, so we have to use 228K pages. And we're specifying that this starts at page 14, and these are indexed from 0. So I think this basically means pages 15 and 16 are used for storage, parameter storage. Unfortunately, it's quite a lot. So it's 256K wasted on parameter storage, but nothing we can really do about that. Okay, and then on we go. So we're saying that we're using data flash for logging, so that's why this is here, and you might see something different for SD card. And then you have to specify, if you remember, we've got serial order from the bootloader, a lot more serial ports this time, but also this is a common pattern, so we want I2C order as well. So this board has one I2C bus, I2C1, and you could see two here, but since there's only one, you just still have to have the I2C order here. Again, we're specifying buzzer, but a few more options around the buzzer. Again, specifying USB, again specifying debug. And then we're on to the SPI devices. So these are the main devices on the board, typically the OSD chip, the IMU, and in this case, flash black box logging. And SPI always requires that you specify 4 pins: MOSI, MISO, clock, and chip select. So each SPI device will have 4 pins. The chip select can be shared, so you can have different devices on the same SPI bus. So we could have SPI1. So these two could actually both be on SPI1, and the only thing that would be different would be the chip select pin. So basically, chip select says this device is active. But again, these are all on separate SPI buses, so we've got 4 definitions, 4 pins per SPI device. And then we've got the definition for I2C, and I2C basically only needs 2 pins, SCL and SDA. This is what your Compass might use, that's an I2C device. And you can see it specifies I2C1 as the device that this applies to. So this is a sort of common pattern, is the last thing in the line is the device that this applies to. So in this case, this all applies to SPI1, SPI2, I2C1, etc. Okay, so we've got a couple of pins for voltage. This is for the ADC, so this is how your flight controller understands voltage and current. And these pins you just specify like this. I should say that which pins these are fully, this is required by the manufacturer, so there's no optionality around what these pins map to or what these pins are on the actual device itself. And typically this information comes from either the manufacturer or maybe from a Betaflight config for the same board. So Betaflight will have pin definitions that map to the same functions. And in fact, I've written a little script that it automatically takes the Betaflight definitions and converts them into ArduPilot definitions. Okay, we'll skip over VBus, and then we've still got the VTX power pin that we want to pull to make sure that you've got power to VTX. We then define some defaults. So you could define these defaults in the hwdef, or you could put the defaults in this defaults.param. So these are kind of read as part of the build process. So these are defaults as well, and you can specify them either way. But it's useful to basically define default setup so that users don't have to configure everything. You wouldn't necessarily need to include this here, but if you don't, then there's no battery monitor configured by default, and so the user is left to set that up. Similarly with RSSI, so this relates to, we've got battery voltage and current sensing on the ADC. Here we've got RSSI on the ADC. And then LED definition, and then we're on to the UARTs. And so for every UART there's basically an RX and TX pin. And so here, this for USART1, and these names, USART1 versus UART4, say, these are fixed by STM32, so sorry, ST micro. So they, if you look in the data sheet, you'll see then either labeled USART or UART, and you have no control over that. So you just have to follow the rules. And you can see we've got 1, 2, 3, 4, 5, 6 UARTs here, and some of them we've specified don't use DMA for these channels. So by default we use DMA, but that also uses up DMA channels. And for some things like VTX, say, very slow protocol, no need for DMA. I can't remember, but I think UART4 might be the Wi-Fi or something like that, so which we don't support, so no need for DMA. Similarly for ESC, I think this board supports BD shots, so no need to support high throughput ESC telemetry. And what you'll see is that each of these appear in the serial order here. So you've got 1, 2, 3, 4. And what I tend to do is I make sure that the UART mapping maps the serial mapping. So this order is what you see in the config. So this is serial 0, serial 1, serial 2, serial 3, serial 4, serial 5, etc. So I could switch these. I could switch USART1 and USART2 in this this order, and that would be perfectly legal. But then serial 1 would be USART2 and serial 2 would be USART1, which is a bit confusing. So what I tend to do is make them match, which means because there's no UART5, we just have an empty slot here. Okay, so onwards. So we specified a few default protocols for the UARTs. So serial 6 typically used for the radio receiver, so that's specified as the default protocol here. Serial 7 typically specified as for ESC telemetry, so that's specified as the default here. And then on to the motors. So this is kind of one of the most important definitions. And the motors, basically you have a pin, you have a timer that the motor is associated with, so timer 3, 2, 5, 8, you can see here. And then this channel is, in particular for bidirectional D-shot, this is the channel that's used for reading. So each of these pins can be assigned to a particular channel as well as a particular timer, and only those ones. And so this is sort of important for bidirectional D-shot. The timer also specifies the group. So when you see documentation that says PWM group in ArduPilot, that means they're all on the same timer. So these two motors, motor 1 and motor 2, are on the same timer 3, and so they'd be in the same group. Similarly, these two here. The other thing to say is for bidirectional D-shot, so bidirectional D-shot, you only need to specify it on pairs of timer channels, either 1 and 2 or 3 and 4. And so here we've got bidirectional D-shot specified on channel 3, which means it's shared with channel 4. Here, timer 2, it's timer 2 channel 2 and timer 2 channel 3, and these cannot be shared, so you have to specify bidirectional D-shot on both of them. And on these ones we don't want bidirectional D-shot, so it's not specified. And then this GPIO pin at the end means that you can use this for general purpose GPIO, and these would be the pin numbers if you did that, if you specified that in config. Most board type flight controllers are Betaflight configuration, so tend to set up the frame default as Betaflight. And then there's usually also a PWM output for the LEDs. Note that for D-shot and LED outputs and bidirectional D-shot, you must have DMA support. So you could specify no DMA on the end of any of these, but then you could only use PWM or one shot or something like that. If you want to use support D-shots, bidirectional D-shot, NeoPixel, which generally people do want, then you need to have these DMA enabled. Okay, so this basically says I don't want to share DMA channels with anything on SPI1 or SPI4. I do this quite a lot for the IMU device because these run at a very high rate. If you're sharing DMA channels, it can block or slow it down, and the last thing you want is delayed data from your IMU. So I tend to do this for the IMU. And then the other thing we got here is data flash. So flash-based logging is quite slow, so it kind of can take the DMA channel for a long time, and so sharing the channel with something else is not very fair on the something else. So generally I say don't share DMA channels for data flash. So here we got the SPI devices. And basically you have to, so we've got the pins defined above. So for SPI4, say, and then you say, okay, I've got an SPI device on SPI4. This is the chip select pin, so that's one of the pins defined above. This is the mode, so this kind of really refers to whether it's sort of active high, active low. This is the low speed frequency, and this is the high speed frequency. So generally it's the high speed frequency that's the important one. And sometimes you might have to lower the high speed frequency in order to, because the traces are too long on the board and it just won't, you get too much noise if you go higher. But for an IMU, 8 megahertz is fairly typical. For data flash, you can actually generally go a lot higher. I've started setting these to 104 megahertz because data flash people put on these things tends to go quite fast. And then also you've got dev ID. So if you've got two devices sharing the same SPI bus, they need to have different dev IDs. But otherwise you can just use dev ID 1. In fact, we could probably use dev ID 1 here. And this will influence what shows up in hardware ID in Mission Planner. And then this name is then used later on for the actual type of the device. So we've got SPI dev MPU 6000. And then we say down here, SPI MPU 6000 is an InvenSense IMU. So this name maps to a driver name. So this might be InvenSense v3, which is another driver name. And it's the same for, I think, OSD and data flash are picked up automatically. So there's no device name for these, they're just picked up automatically. But for the IMU, you need to specify what kind of IMU it is so that you get the right driver. And then for the IMU, you also specify a rotation, which there's lots of rotations involved. And then a few definitions here. So allow to arm with no compass, probe external compasses. Sometimes people define I2C, but they say, oh, my compass doesn't show up, and that's because we're not probing, so you have to tell it to probe. And then I2C internal mask. I forget what that is. It's something to do with what the bus that's inspected for internal usage. And then final device here is the barometer. So the barometer is on I2C. So you basically say this is on I2C. We specified I2C above. This is the driver type, BMP280. So you need to have a specific driver here. And then this is the I2C address. So bus 0. So I2C1 that would be. Address OX76, and so this is usually specific to the device, and so you can copy that from somewhere else. And then finally a little bit of OSD config. We've got an OSD chip, so let's enable it. The default type is analog, include some fonts. And then finally this is used when you are using advanced timers. So generally advanced timers 1 and timer 8 are advanced timers, and so if you're using timer 1 and 8 you have to specify this. And that is it. So bit of a whistle-stop tour. Hopefully that shows a little bit more, and hopefully you found that enjoyable. Thanks for watching.